So that's the pre-processing, and no, we haven't done any statistics yet, so we haven't tried to make any inference. All we've done is tried to make our brains all in the same space, and then all within each subject, and then all in the same space between the subjects. And then what we do is actually simple correlation analyses. So we really do simple regression. And all we need to do is tell our software what happened, so what kind of trial, was it an easy trial or a hard trial the subject was doing, and at what point in the scan sequence that happened, which of these images we're going to be particularly interested in, and how long it lasted for. And normally, that's what we tell the software, and the software does the rest. In particular, it accounts for this slow time course of the bulb response. So remember, the bulb response takes that 6 seconds to peak and 16 seconds to 32 seconds to come back down to baseline. So there's a complex set of statistical procedures in order to take that into account. And what we actually get at the end are what are called parameter estimates. So this is the statistics bit. So let's just go through that very quickly. So we're using normally a general linear model, which is simple correlation or regression. And you can see a scatter plot there at the top where we've got a pretty bad fit to the data. So the line there, the best fit line, the red line, which minimizes the distance of each data point away from that line, that has a slope which is pretty close to 0. So it's basically a flat line. So we can basically say there's no relationship between the x and the y-axis there. And there shouldn't be, because when I told the graph program to draw it, I asked it to do a set of random numbers, basically. So that's an example of where we've got quite a low slope. On the second one down, you can see that the fit around the line is very good. But it's actually not the fit around the line that we're really interested in. It's actually the slope of the line. So you can see the red line there has got a nice strong slope, probably something like x equals y. So if you've got the x coordinate, it should be fairly similar to the y coordinate. And what you can see is that we've got a pretty good slope. So what we're actually measuring here is the slope for a particular condition in the task. Did it make the brain response go up or down, and can we predict in which direction that would happen with any degree of certainty? So we take that slope. On the bottom, you can see I've got a slightly different slope, so still a very nice fit around the line, but the slope is a little bit less. And so that's actually what we're making our inference about at the end of the day. When we come to do the group studies, what we have to do is take some kind of statistic that is a summary of the response for each of the individual subjects. But unfortunately, it turns out that turns out to be very, very complicated. So the summary statistic that people take are actually what are called betas, or parameter estimates, which is the same as saying the slope of that line. So you can do statistics on the individual subjects, but normally if we're interested in making inferences about a whole population of people, we'd like to do our statistics across the whole group of people instead of just doing it subject by subject. So that's what we're going to do. We take these parameter estimates, or betas, or slopes of line, as summary statistics to the next stage. So we actually get these as images and then combine them in the group stage. And of course, if we're looking, for example, in psychiatric patients versus controls, we have to do this. So remember, we've got our summary statistics, and the question that we're asking basically at the second level, at each individual little voxel in the brain, so every 3 by 3 by 3 millimeter voxels, is the beta, i.e. is the slope of that line from the first level analysis, the subject level analysis, consistently greater than 0 across subjects. So typically we'll measure that with a very simple t-test, straightforward statistical test, just like you might do any other form of statistics. And then we'll represent the value of that statistic in terms of a color on a map. So what do the blobs mean? The blobs mean statistical values. They don't represent activity. They don't even represent the parameter estimates that we got from the first level. They certainly don't represent the bulb response or the blood flow. What they really represent are statistics that came from the combination of previous statistical values from each individual. And I think that's really important to bear in mind, because it's often easy to forget that the blobs that we look at on these marvelous images, which are so attractive when we see them on websites or in the newspaper, that's all they represent. They just represent the t-statistic normally. So you can see the coloured bar there, which goes from about 0 to 20 in this case, because it happens to be a very a particular type of brain activity that is very consistent across subjects. You can see that the warmer the value, the closer it is to white, the higher the t-statistic. So those of you who are familiar with statistics probably know that a t-statistic of about 2 represents a p of about 0.05, or a 1 in 20 false positive rate. So actually here the t statistics are very impressive. They are up above 10 or 12 in some cases, and that's because this is a very, very reliable effect across subjects. You can see if you plot out the individual parameter estimates that I've done on the bottom right there, every single one of them is greater than 0, and they're very consistent across subjects, and that's why you have a very large t statistic. So that's all that the blobs tell us. They tell us that there was an effect across subjects in a particular direction. Okay, I hope that's clear. So, what are the complexities? Well, the first complexity to notice is that, of course, we've got 30,000 measurements going on normally. So if we've got 3 by 3 by 3 millimeter voxels, so you can see, you can probably just about see the, 1 minute, okay, that's fine, the little squares there. And so each of those is actually a separate measurement. So if we take a given statistical threshold, like a 20% false positive rate, p of 0.05, that means every so often we're going to get what looks like an apparently significant result just by chance. And we do need to control for that problem appropriately, and it's actually a slightly complex statistical issue to get around. Though most software packages will do this for you, but that doesn't necessarily mean that just by looking at this picture you can determine whether that something is statistically reliable or not. You really do have to look at whether they've appropriately controlled for this multiple comparison problem. Just to reiterate it, the more times you do a statistical test, the more likely you are to get a result just by chance, and you can imagine how that could happen very easily. In terms of psychiatry, we've got a very important confound, which is that they often take drugs. So some medications don't just affect the brain's response in terms of the cells, but it also directly affects the brain's blood flow. And that changes the thing that we're actually trying to measure. So you can, inadvertently, if you give a patient antidepressant, for example, directly affect the constriction or the dilation of the blood vessels. And of course that affects the hemodynamic response. And it might affect the hemodynamic response without actually affecting the underlying neural activity. And that's a very important confound. Of course, medications will also affect brain activity. That's why we use them, to try and make patients better. But a separate issue is that they could accentuate or mask an effect that's actually related to psychiatric disorders. So you could create what is really a misleading result out of nowhere. And so there are two things that I want to take home for messages from this slide. The first is the importance of looking at unmedicated patients as well as medicated patients to control for the medication effect. And the second is to not believe brain imaging studies the first time you read them, only the second or the third time you read the result, because replication is very important. So here's an example of medication effects, a great study by Kumar et al. In Brain from last year, and they were actually trying to look at the effect directly of antidepressants. So this is patients with major depression, and you can see, so the top left picture is the control sample, and the top right picture, C, is the patient sample. And you can see there's this area that I've circled in red, which is the anterior cingulate cortex, and you can see that effect is absent in the patients relative to the controls. All very well, you might think. But in the bottom right panel there, D, they actually put their controls on medication. So they gave their controls antidepressants as well to see what would happen to the bold response. And as you can see, you get a very similar effect to looking at the patients who are currently depressed. So this suggests that it's actually the medication that is changing the brain's response, the hemodynamic response, remember, and maybe the brain activity in the patient, and not necessarily the disease itself. And that's a very important thing to remember. So I hope I haven't gone too far over time. I want you to take away the message that we can analyze complex brain activity, or rather hemodynamic signals related to cognition and motion, and we can hopefully improve our understanding of the brain in health and disease. But the analysis is complex, and because of the number of multiple comparisons, if we don't control for it appropriately, the false positives are practically certain. So you really need to pay attention to studies that have been well replicated. So thanks very much for your kind attention. I hope to take questions.